big audience here, yeah, this is the next in our series of inaugural lecture, and we've got the privilege here today to welcome our Vice Chancellor, Professor Paul Boyle, who will make the introduction. So over to you.
Thank you very much.
Thank you.
Well, good afternoon, Pranandar, everybody, and thanks for turning up to this. Inaugural lectures are an absolutely essential part of what we do as institutions, just recognising our colleagues, the position they've moved into, and of course all of the work that's led to that position. So we're very much looking forward to this. I'm pleased to see that the faculty is doing such a good job of these. It's a bit more sporadic around the rest of the institution, so I'll be encouraging across the whole institution to follow your lead. Today we're here, of course, to listen to Haddad Khodaparast's inaugural lecture. It's a fantastic opportunity, of course, for you to hear some of the activities that he's involved in. I'm sure many of you are already fully aware. I have to be absolutely honest with you. When I read through the briefing I've just been given, I'm hoping I understand a lot of this better after the lecture than I probably do now, because I'm not sure I know an awful lot about the semi-aeroelastic Hing Albatross 1 project in Airbus, or indeed the problem of gust load alleviation using movable winglets. But I'm sure I will do by the end of the presentation. Obviously, you have a huge experience, extensive experience in structural dynamics and methods development, stochastic model identification, I think, in particular. So a lot of work that our institution has a history in, and I'm sure that the work that we've been doing here for decades, if not up to many, many years beyond that, is work that's built upon the sorts of things that you're now going to take us even further and build our reputation even further. So I'm not going to say any more other than to say I'm really pleased to be here. I'm looking forward very much to the lecture. And as I say, I'm sure I'll understand an awful lot more about it after we've heard from you than I do at the moment. So thanks very much indeed.
Thank you very much. Thank you very much, Vice Chancellor, for the nice introduction, and also thank you everyone for attending my lecture. Although I mentioned gust load alleviation and also Aeroelastic simulation, but I'm going to concentrate on more specific context, which is like stochastic model updating, which is one of my expertise, which has been developed during the years. But I will also mention about the extension of this work into aeroelasticity, obviously. So this is the contents of my talk, and you can see I cover several subjects. But I first start with introducing myself. I graduated from Sharif University in Iran in 2002. And I immediately appointed as a vibration engineer. Sorry, I forgot to turn off my mobile phone. So, yeah, I started as a vibration engineer in Industry Research Center. I actually searched for a picture, and I found a picture of myself in 2004. And what you can see is this is about 18 years ago. And what I was doing here, I hope that I can explain in the following slides what I'm doing here, but you can see me hammering a chassis frame with a hammer, which I will explain a little bit later. I'm measuring basically the response of this structure chassis frame with a system of data acquisition called LMS. I'll come back to this picture later, but I started my PhD in 2007 in Liverpool, working with well-known Professor John Muttershed, and finished that in 2010. And then I started a postdoctoral position at Liverpool, then joined Swansea in 2012 in Aston, working with Professor Hans since. And then my first academic job was in July 2013, and I was appointed as a senior lecturer. And since then, I have been involved. I have won several grants. The most prestigious one was the Royal Academy of Engineering Fellowship in 2000 which I worked with Airbus. And more recently, I was co-PI and PI working with Professor Friswell in EPSRC Digital Twins for Improved Dynamics Design. And you can see that I was promoted to Associate Professor in 2019, and then this year to 20 in Professor. Right, so before I start my talk, I would like to give you a little bit of flavor about what is the role of models in engineering design. And what you can see here in the right-hand side is what we call traditional V cycle, which basically represent a process of development and testing a structure, a physical structure. And this was basically called traditional because there is no modeling involved in this V cycle. But you know that nowadays, like all areas of modern endeavor, the engineering is also taking advantage of computational models in the engineering design and also over the life of the structure. And that's what actually represented in the left-hand side diagram by basically Dan Seal from Airbus, which is the concept of model-based system engineering, or MBE, the diamond model, which the bottom V is basically the traditional V cycles when you have the development and the delivery and manufacturing, which is all dealing with the real structure, with the physical structure. But what is added to this is the modeling, which can basically run in parallel with the delivery of the structure. And in basically this circle in the middle is basically shows that the interactions between the model and the structure, which is basically used in order to inform the decisions that an engineer make about the structure using the simulation and modeling. And obviously, the models has many advantages in the design process, and as you can see here, the computational models can be used in all engineering domains. Can be used in order to improve the efficiency and make the design much more cost-effective. And it's basically a prediction tool that can be used to evolve over the time. It's basically can be used for different applications, such as structural health monitoring, that you can actually consistently check the health of the structure. There is a concept called digital twins that has been introduced for many years. I'm sure all of you have heard about digital twins. It basically can be considered as an enabler for model-based engineering design. And the concept introduced by Professor David Wagg in this paper is basically to extend the V cycle to the W cycle, and you have the prototype design stage, and then you use the digital twin model in the detailed design steps as a kind of a cycle that can be informed again the decisions made about the models. And this is also shown in other concepts, but looking at the literature, what you can see, there is no consensus about the definition about digital twins. There are lots of definitions, and every company, every university groups will have their own definitions. And perhaps the first use of the word of digital twin was basically given in this paper, which is NASA and US Air Force in 2012, when they basically introduced a digital twin is an integrated multi-physics, multi-scale simulation of a vehicle or a system that uses the best available physical models, sensor updates, fleet history, etc., to mirror the life of a corresponding flying twin. And I like the word mirror here because I think that's a better definition for our application, as also introduced by Professor Keith Warden in his paper, to suggest to use the word mirror instead of a digital twin. And what the mirror is, basically, actually in this paper you can see Professor Warden has described a mathematical definition of the mirror. That is basically you have a physical structure that can be represented as S. This could be a car structure, any structure. And then you have E, which is any all physical reality exterior to S. And then you have a context C for S for modeling some aspects of S, and also a schedule W for the context C. And then the important thing here is that you have the response, which is coming from the physical structure, which is called T, and also the simulation, which is coming from the model. And basically, what is about the mirror? The mirror means that it only provides information about the mirror facing, what is basically shown by the mirror. It's nothing beyond that, and you don't get any more information. And that basically depends on what aspect of that structure is basically going to be important for you. And to bring this in the context of my research, this all kind of very abstract word, is basically that concept of mirror can be very simply represented in this diagram, where you have a physical system. Obviously, there are environments that can change your physical system, and you have an input to the system, which I will explain in my application, dynamics and structural dynamics, what is that input. And then on the other hand, you have the model, and the expectation is that if you put similar inputs to your system and the model acts like a mirror, reflect what you can see in the reality. So that's basically the idea of the mirroring. And it's been developed actually since 1970s. The methods called finite element model updating, validation, different names. And actually, the interesting thing is that the first book, which basically provides a very good survey of all the books, is written in Swansea in 1995 by Professor Friswell and Mottershed, who basically is now a reference in this area. And it's a very common now procedure in industry to basically follow this method to basically update the numerical model. And in terms of the research, there is probably not much to add to what is available, and it's been actually used many years. Before I go through my research and say how this concept is used in my research, I told you about the first picture of myself, and now I'm going to talk a little bit about what we do in our vibration lab or dynamics lab. And there are lots of works, obviously, we're doing, but the simplest one is the model testing. And you remember about these previous diagrams, I talk about input and I talk about the output. And the model analysis and testing is a process that we basically apply a force to a structure and we measure the response of the structure by accelerometer. So that's what we do in the model testing. And if we assume the structure is linear, which is more or less the assumptions they make in industry, then your ratio of the output to the input represent a FRF curve, which is the response in the frequency domain, which shows some peaks at certain frequency, which we call them natural frequency or resonance frequency. And they are independent of the input and the outputs. They only represent the properties of your systems. The input, which here you can see it could be a hammer or it could be a shaker, that you basically measure the input by something called force sensor. And the output could be accelerometers or a vibration sensor, a laser displacement or laser vibrometer. We have all these equipments in our lab. And as I said, the important point is if the structure is linear, these curves will become independent of your input-output. The ratio will always is constant and represent the properties of the structure. So then, just to explain what is the resonance frequency for those audience who are probably not familiar with the structural dynamics. So basically, we have two types of force, as you know, static force, which the force will only apply to the structure or to the object without any frequency. And obviously, as you increase the level of the force, you would see more effects like more displacement. So the very simple one, I apply a force here, I will get the displacement. And as I increase the force, the displacement increase. But the force could be a sinusoidal force, like a frequency associated to the force. The level of the force can remain constant, but the frequency of the force can change. And if you apply that force using a shaker into a very simple plate, as you increase the oscillating frequency, you can see that at some point you will see a great jump in the response. And that's the point in the frequency domain, the natural frequency. And each natural frequency of the structure corresponds to a shape. And you all live in Swansea, it's a windy city, and you probably see lots of beams vibrating in the streets. That's basically the first bending modes of those columns around yourself. And that's basically the first resonance frequency. As you go to the higher frequency, you could see more complicated shapes. And depending on the excitation frequency, these shapes can be more and more complex. But normally, we don't excite the structures with those high frequencies. And therefore, we only consider a certain number of modes in our analysis. So that's hopefully give you like a little bit of understanding what we mean about the frequency and resonance frequency. And now going back to the concept of the mirror and its application in model updating. So I mentioned that you have a physical structure, and we can do a test in the physical structure. And obviously, there are lots of uncertainty associated with those tests. You have to repeat the test. But normally, if you assume it's a single structure, which is tested in a controlled environment, so you control temperature, everything. So you expect, if you measure, for example, only two natural frequencies, only 1 point in the plane of the first and the second natural frequency. That's what you expect. Obviously, in reality, you have to do a lot of statistical analysis to end up with this 1 point. But let's agree that this point is a representative of the first and second natural frequency of the structure. So now we want to make a model which basically represents these test data. And obviously, we use our knowledge. We make a computational model of that real structure. And this real structure we simulate the real structure, and we get a point in the same plane, but not obviously at the same location of the real structure. And now the question is, what did we do wrong in terms of the modeling that we see these discrepancies? And that's basically the question is going to be answered by the researchers in different ways. Obviously, the computational models always say we increase the fidelity of the computational models, and we can then include more physics to basically minimize these discrepancies. But that's not the case always for all the applications. So, for example, in our particular applications, which I will talk later when we talk about the structural joints, you can't really make any detailed computational models which represent all the variability and nonlinearity at that micro scales. And I will come to that point later. But as I said, in industry, this is a normal process. They make a model. There are some parameters in your numerical model. They try to adjust and tweak those parameters and minimize these differences. What was my contribution during the PhD and postdoc was developing methods to basically consider multiple structures. So I mentioned that we consider not only one structure. If you consider a car coming out of a production line or aircraft structure, you don't have one car, you have multiple number of cars, all with the same design, and they all try to basically manufacture it in the same way. But eventually what you see, if you do the test, minimizing the uncertainty for every single structure, you don't end up with 1 point in that plane. What you will get is several points. Moreover, this structure is supposed to work in different environments. So you make an aircraft, it's going to fly in different countries with different environments. So those environmental parameters will also change your structural parameters. So the question that I basically tried to answer was then the same plane, but now we have multiple points, which is, we call it the clouds of frequencies, which, as I said, this could be representing the variability, not only due to the different multiple structures, but also due to the environmental variability. Now you have to make your model which predicts these scatters. And this is where we introduce a stochastic model updating. That's where SMU will come into the place. And this paper, which is written by myself, Professor Motorshed, and Professor Frieswell in 2008, was one of the first papers which described this concept. And the objective in here is not only to minimize the center of these clouds and also to minimize the size and also the orientation. This is a little bit of details in the statistics, and I'm going to just skip that. And there have been many methods that are developed for stochastic model updating, mainly in the linear structures, and there have been several papers that have been published. Some of them are here, but many from other institutes. But amongst all those methods that have been developed, Bayes' theorem proved to be the most powerful technique in our application, which is actually shown also to be very useful in other applications. But because its theory is going to be probably a little bit out of scope in my presentation today, I'm going to give a very simple example that I used it in 2020 for COVID-19 application. It's not engineering. And hopefully that gives you a bit of understanding about the concept. So what's the Bayesian theory? Is the Bayesian theorem as it's explained here. You have some proposition about the world. So that's basically, could be, I'll explain what is that. And you would have some data. And you have some prior distributions about that proposition, about the world, which we call the probability of that proposition. And then you have also some data, which could construct your likelihood function. And the denominator of this one is the total plausibility of the evidence. And based on that, you can improve your confidence about the probability of that proposition. And as I said, I'm going to just say this in a very simple way in the example that I did, and I sent it to NHS. I'll tell you a little bit about the story, why I did it. But basically, you have a prior distribution which only reflects our beliefs before we see any data. But this slide is something that I put it exactly in the same way that I sent it to NHS. And I will explain a little bit why I did that. But the main idea was, what is the probability of false negative test results for COVID, false negative? And the probability was important because during those days, NHS has a policy that they only do a single test for everyone. And my idea was this needs to be repeated at least once or twice for key workers, because my wife was a key worker. She was tested negative. She had all the symptoms. So that was the reason I come up with this idea. And hopefully that gives you a bit of understanding about the method. So going back to the proposition we have here, our proposition here is false negative. If I ask you, before seeing any data, before having any information, what is the probability that you assign to the false negative test results? Anyone?
5%.
Could be 5%. Yeah. It really changed from one person to the other. I would do it 50-50. Because when I have no information, it could be 50% to be false negative, 50% to be false positive. So it's basically something that when I don't have, basically the best starting point would be 50%. Then, in the denominator of this one, we have the total plausibility of all the evidence. Basically, you have 4 conditions here: false positive, false negative, true positive, true negative. So that's all the total plausibility, and you can calculate that. But if you start with the 50%, then we need some information. As I said, in our applications, we do tests. I searched a little bit in the web, and I found this link provided some information that I can improve my confidence about calculations of this probability. This link has this sentence: the reported rate of false negative is as low as 2% and as high as 37%. So we have a range for the probability. So I define 2 scenarios. One is the worst case, and the other one is the best case. So and I do all these calculations, which is simple calculation. So I'm going to repeat that, and I show this curve, which is the important one, and it's very intuitive. It's basically saying to me, my starting point before doing any test is 50%. When I do the first test, based on the information I have, in the worst case scenario, the probability of the false negative in the worst case obviously reduced to 37% because this is only based on the information. In the best case, reduce almost to 0. So NHS take the best case always. But if you take somewhere in between, let's say in here, then probably we need at least 1 or 2 tests to reduce this probability of a false negative to a reasonable value. And hopefully that gives you understanding of the concept of the Bayesian theorem. And in our application, which I going back here to this slide, we use this application for using experimental test data to improve the probability of the parameters that you're going to assign into the stochastic model that predicts that probability of the measurement data. So that is the whole idea, to give you the big picture. And this is the equation. I promise that I won't go to any detailed equation. So you can see that it's a similar equation, but the application is in engineering and in the structural dynamics. So the pioneer of this idea is Professor Beck, who actually introduced his first paper, but our contribution was the extension of this method to the case of SMU again, or stochastic model updating. And there are some slides here, again, about how to estimate your prior and how to calculate. Obviously, when we're dealing with the models, you can't really just use simple calculations like multiplication. You need to use computers to basically calculate all of these analysis. And I just show here some of the things that if, for example, you know the posterior is normally the method MCMC, which is used to identify your posterior. The posterior and prior, again, I have to clarify. Prior is what you estimate. The posterior is basically the improved probability, and you can actually do this in an iterative way. Okay, so let's move on. I'm going to just show you some of the results that we got from these methods that we have developed. This is a collaboration with German Aerospace Center that we basically wanted to demonstrate the application of the methods that we develop in this area. And when it comes to the academia, we basically have limited resources, so we can't really do test in a very complicated structure. We have to basically make benchmarks to basically test our methods or ideas. And this is what is called DLR AIRMOD structure. And what they try to do is to see what would be the effect of different sources of uncertainty in the vibration test data. And they found that assembling and reassembling the structure will have the maximum effect on the variability. And what you can see here is some data on these natural frequency that I mentioned. And in reality, every structure has infinite number of natural frequency. But as I said, in reality, we're only dealing with a limited number of the frequency, in this case 30. And you can see the variability due to the assembly for different assembly and reassembling structure. And we have now a model which basically mirror or reflect the physical structure. And we assume that there are some parameters within this model that we are not sure about, and we want to basically adjust them using different methods that we try. When you do the experimental model analysis, you can extract the mode shapes. These are the mode shapes of these aircraft structures. So every structure has its own mode shape. So that's one of the also analysis that is carried out in reality. And as I said, in this one, we use 14 sets of measurement data for the methods that we develop, and we basically demonstrated that the method can basically predict the scatter of the data from the experiment very well, both covariance and Bayesian. But the advantage of the Bayesian was that you can also see some of the things in the input parameters, the probability, because the covariance method that I did develop only could show the range, the variability in the parameters, but the Bayesian, you can also identify the probability of the input parameters in the model. And that becomes sometimes very important, especially when you have model behavior. I mentioned about the joint. So as I said, there has been many methods that are developed in the past decade, and it's mainly concentrated on improving the efficiency of these methods. But one of the questions that remains always in the literature is, where is the source of the uncertainty in different applications? Where is that doubt come from? And in our application, obviously, we know that a structure is made of different parts, and they all assembled. And this assembly process can bring variability in the results. But also, when you have the joints in the structure, which simply represented here, the joints can also cause nonlinearity in the response. So I talk about the linear response. I talk about that the output to the input ratio remains constant. But when you have the nonlinearity, that constant assumption is no longer valid. And what will happen is you have some stuff like frictions or slipping between the surfaces, or you can have separations between the joints. And that all those phenomena can create nonlinearity. And then this nonlinearity will result in input-dependent natural frequency. And last year, with Nidal Jamia here, we organized a workshop in structural joints at Swansea. And I like this graph from Professor Crack from Haddad University, who basically described the concept of the resonance frequency dependence on the input force. And in this graph, you can see three parameters. The response, I mentioned that is measured by accelerometers or other sensors. The input force, which is the excitation force, and the frequency. So you have three parameters here. At low-level excitation force, you can see the variation in the resonance frequency is not significant. That's where we can assume the structure is linear. You increase the force here, you measure the response, the ratio always shows one single frequencies. As you go to the nonlinear regimes, by increasing the force level, you can see this curve, which is called also backbone curve, will basically bend in different directions. And this bending is dependent on what is the type of the nonlinearity. And as I mentioned, this will make the problem more complicated, because now you have something which is related to the parameters of the system, but is not dependent on the input as well. With my colleagues and my PhD students, we have published several works on what we call deterministic. So again, consider that now the response for a single structure, instead of one point for one frequency, is a number of these curves which are called backbone curve. And now you have to use this backbone curve to modify or identify the nonlinear model in the structures. And these are a list of papers, not us, many other groups working on it, to basically develop methods for what we call deterministic nonlinear model updating. And it's still going on. But in my EPSRC project in 2017, we actually say it's too early to move into the nonlinearity, and we still have a lot of lack of knowledge, even in the linear structures with the joints. Because I mentioned about the difficulties in modeling of the joint structures. And the reason is because you have a randomness in the asperities that contacting two surfaces. And this randomness could be completely different from one structure to the other. And it's almost impossible to model this at the microscale. And we basically proposed the idea of making equivalent model which can represent this randomness in the microscale, but is still dealing in the linear regions. And in order to test this idea, we make 4 surfaces. Again, we have limited budgets. It's better to make as many as you can, but that's what we could do. 4 structures, and basically with different surface roughness that we could measure those surface roughness. And we did like the experiment. And apart from the modeling, that I'm not going into the details, we could see great variability, not only in the frequencies of the structures, but also in the damping ratio, which is also another important aspect. And we published a paper in JSV, one of the most prestigious journal in the field. And that work was continued to basically doing this experiment on different sets of structure by like 25 different combinations of these simple lap joints, still assuming we hopefully only excite the linear modes, and changing the preloads on the structure and repeating the hammer test. And that's like 75 tests, but not only 75 tests, because every test has averaging. So you have to imagine every test takes 10, at least 10 averaging. And Hadi here in the lab was in the lab during those times to do all these tests, and it took about 20 days to complete. And these data, which are coming from that exercise, are quite useful because they're showing the frequencies of this simple structure, but not only the frequencies, but also the scatter of these frequencies. And you can imagine these results are quite intuitive, because what you can see as you tighten the bolts, you stiffen the structure, and the stiffness will increase the natural frequency. So you can see that the center of this scatter moves and shows the increase. And that's not something to surprise, but you can also see that the level of the variability and uncertainty reduced by these data. As you can see, the size of this scatter reduced. And these are real experimental data. It's nothing from the model. On the other hand, we saw something in the damping that by reducing the preload, basically on the joints, the uncertainty in the damping ratio, or the variability in the damping ratio, will increase. And as you tighten up, the variability reduces. And we basically say that, okay, we can use the computational model and we use the Bayesian updating approach, and we show that the method can work well, especially in the low frequency regions. And we publish another paper in MSSP. So I'm going to talk a little bit about the work that we are recently doing on this. And basically, as I said, with Dr. Nidal, who is also here, he's a research officer at Swansea University, we have done a lot of work in modeling on nonlinearity and also identifying the nonlinearity in the joints. But this was quite an interesting exercise that basically designed to show the level of the uncertainty in the modeling of the very even simple structure that you can see here. So what was the task? The task was basically designed to do a blind prediction of the nonlinear dynamic response of a system. So what you can see here is a simple plate bolted in two ends, clamped in two ends. And basically the goal was different institutes, including Swansea University, we are part of the structural joints community, to perform their own modeling with the data given to them and provide estimations of the damping and frequency. We only reported damping here. And you can see the great variability only in the dampings from different institutes. And it basically shows the level of the confidence that we have sometimes in the model is kind of very low, especially for a very simple model like this. Obviously, the one that is used, a very detailed model, was Sandia lag. And what they did is basically last month, several researchers from us, Dr. Nidal, went to Stuttgart, spent about a month to do a lot of interesting experiment. And this is the test rig that shown in their institutes. And I think we are trying to also make something similar in Swansea at the moment. And the idea is now we basically measure the mod shapes. You have three different basically plates, which are basically attached here. And you can see all the sensors which is used for the measurements of the modes and also natural frequencies. But what is important here, these are again all experimental data. And what you can see here is again something which is a backbone curve. I mentioned that the natural frequency, this is W hat, is the base level of the base excitation. So instead of force, you increase the amplitude of the base. And as you increase the base excitation level, you should see some nonlinearity. Initially, the natural frequency reduced because you have some frictions, some loosening in the stiffness. But then the geometric nonlinearity, which is a hardening nonlinearity, will become dominant, and you can see an increase. But In the frequency, you can see in the linear regions, you have still a variability in the three structures. And that level of the variability increased as you go into the highest levels of the input excitation. The same happens with the damping. The difference is damping is always uncertain because the range of variability is always quite big. So then, after doing this test, all different universities basically put the damping ratio together in one graph and compare that with the experiments. And these are the list of universities you can see under this table. And magically, our predictions came very close to the experiment. And as Sandia National Laboratory estimation was also close, although we were not very good at estimating the frequency. But what you can see here is not a single curve. So I mentioned that what we are doing now is the deterministic nonlinear model updating. So we're trying to basically develop a model which represents what we can call the mean of this. But in reality, this scatter in the nonlinear regime is meaningful, right? And the idea is to develop methods now, and this is the current research, which not only our groups, many groups are working, to develop methods that can predict also this variability in the nonlinear region. So that's basically the whole idea. And the Pushpa Pandey, who is basically also here, she's also working on the idea. We come up with the idea of defining the likelihood function in Bayesian approach by basically fitting a PDF on different locations on the backbone curve. And Pushpa actually presented this work 2 weeks ago in ISMA in Leuven for the first time for her to present her work there. And we show some results, but not using experimental data. This is only simulations, but we use simulation to produce data to basically show that the method is working. So that's all about structural dynamics, which we talk about. So now I come to aeroelasticity, which is also my interest. And this is the work we did with Airbus and also in Swansea University, Winton. So Davide Balati, who is a PhD student, I'm sorry, there seems to be something here. Okay, his name is Balati. The idea he actually started in Airbus that, we have now lots of advantage of having high aspect ratio wings. It can save fuel, and it can also improve the lift over drag ratio significantly. But then there are limitations on the airports because as you increase the length of the wing, then the aircraft might not fit in many places. And what you need is a folding wing. So basically, once you land it, you can fold the wing and then basically fit it to wherever you want. The idea started in Airbus, as I said, to say that why not we assume that the winglet can basically move when the aircraft encounter the gusts. The gust is something you all probably experience while you are in the aircraft. You basically experience the effect of the turbulence, which is not really pleasant. It's quite annoying. And you would like to basically minimize, as a designer, those effects on the passengers in the aircraft. And you need something like isolators to remove that. And the concept shows that if you can lock this wing and then just release it while you are in the aircraft, it can actually reduce the load. But whether you sit on the aircraft with this moving airfoil is another question. It's going to be very scary looking from the window and seeing that the tail of the aircraft is moving. But the idea is just letting it move during the turbulence, not all the time. You can have a mechanism to lock it again. And with Davide, we have also collaborated, and we actually built a demonstrator in Swansea wind tunnel data. So the first thing was what we have in Swansea wind tunnel is a flow which is not perturbed. And the turbulence is due to the movement of the air up and down, which basically causes turbulence. Okay, so we need a device to design a device which basically oscillate the wave in the wind tunnel, and basically these two vanes will do that jobs. And this is the demonstrator here. On the top of this, we have laser sensors, which we measure the displacement at different locations. And it's been actually shown in many applications this can work, but as I said, it's mainly still in the low technology readiness level. It's not something that we can now build in. There's still a lot of investigation going on. And I mentioned about how to produce the gas laws. So I mentioned this is a smoke test showing that you have two vanes. You can actually input any kind of motions to the vanes, and then it can basically oscillate oscillate the air, and that oscillation can basically cause turbulence in the wing. This is like what we call 1 minus cosine. So we just excite the winds with the 1 minus cosine. But you can actually input any other functions you want to the wing. Going back to the concept of resonance frequency that I mentioned, it's something we always use, is the frequencies of the wing, which is shown here. In the aeroelastic case, when you have the wing and the air together around it, will become a function of the velocity, right? Even in the linear case, even if they have their linear structures. And as an aircraft designer, you have to always make sure that your aircraft is free from flutter. The video I'm going to show you here is just probably 2 seconds of the wing fluttering in our wind tunnel. And what David tried to do, once we saw that, he basically reduced the speed of the wing to basically move away from that flutter. And this is the graph. So you can see the frequencies are changing as we change the airspeed. And in this video, we go the other way around. So we show the flutter, and then we reduce the frequency. So that's something you don't really want to see in the aircraft. And then when you reduce, you can see that we go to the steady state condition. Okay, so I think I come to the end of my talk, and I'm just going to give a few words about the Swansea Vibration Lab, Dynamics Lab, and Wind Tunnel Lab. We have lots of equipments that I hope that these presentations can create some common interest. Obviously, with the IRIs, we can also talk to the other colleagues to see if there are common interests, and also all these expensive equipments can be also used by other researchers in different departments, and I think the idea of the faculty could help this very well. You can see pictures of the scanning laser virometer. Dr. Azizi, who is an impact research fellow working with us since last year, has basically used this, and you can see some examples of how this scanning laser virometer can be used to measure the mode shapes. We have the lots of shakers, base excitation shakers, APS, and all other sensors like lasers, displacement sensors, and scanning, as I said, which can be either used in the wind tunnel or in the structural lab. I'm part of the Aerospace Engineering Structure Research Group, which used to be led by Professor Frieswald. And there are also lots of other activities going on in our groups. That includes morphing wing tip, wind tunnel experimental aerodynamics, SHM or structural health monitoring, vibration of MENS, Hadi and Saber are mainly doing flight dynamics, VA is working, and also Shakir and James, who are working on active and passive aeroelastic vibration loads. And I would like to thank all the people who basically worked with me in the past few years, and some of them are now working in different organizations, either as a lecturer assistant. I think that's very good to hear that the people people who work with you progress in their career and basically move on to the next stage of the academic development. And I would like to also thanks to all of my line managers, mentors, and advisors in the past 12 years. Unfortunately, I lost one of them. The second one passed away last year because of the COVID. And I would like to also say my great acknowledgement to Professor Frieswald, who was here and helped me during the last 10 years to develop my career. And thanks to all the other mentors and advisors. And thank you very much for your talk, and I hope that gives you a little bit of flavor of what we are doing in our research. Thank you very much.
Thank you very much, very interesting. Many things in there. I'm pleased that you publish in my journal as well. So and that you beat Imperial College in your model. We haven't got much time for questions. Are there one or two questions which we could look at? Okay, Rashesh.
Yeah, for Sumit, congratulations for the point that you explained these difficult concepts without using buzzwords. And I think the credit goes to you for that. My only assumption is that when I work with aerospace industries, the CPK values are very high, and therefore it will be called as a common cause variation when you apply your Bayesian analysis. And what I learned that the Gaussian approximation doesn't really hold because of nonlinearity and everything, and therefore we have to change our models. What's your experience when you do this tolerance limit optimization? Do you need to consider that effect, or it's still a valid assumption?
Yeah, I think that's a good point. I mean, in many cases we assume Gaussian distributions because of the lack of data, and it's the simplest model to use and to start. And also there are lots of mathematical methods that are developed already. What we have tried to do is to avoid that and try to just use the raw data and fit whatever it is, the PDF or probability distribution function to those raw data. And obviously that could somehow overcome, but the problem is always the limited amount of data. And you have to basically say that even these fitted PDFs could not be very accurate. And I think like all other applications, the limited availability of the data is a big problem.
What about missing data?
And the missing data is another one, yeah. And it's something that we also say that about the validations. When we validate a model and we use it, there are data which basically come in the life of the structures, which, as you said, there are missing data. And the question is whether this model can predict those data or not. And if it can, we can actually say it's a validated model. That's also another thing. And in our practice, we measure like 30 natural frequency, like the example I mentioned, German Aerospace Center. But we don't use all of them. We use limited of them. And then we try to see whether the model can predict those unseen data or the data which is not used in the updating process. And that's somehow improve our confidence. If there is still a good argument, improve our confidence in the arguments in the validity of the model.
Okay, thank you. I think we have to stop it here now. Very interesting question and answer. We've got a little plug for you, which we'll hand you over to remember the day. So again, congratulations.
Thank you very much.
Very good presentation, and we'll come for a photo shoot up here in front of our partner. So again, thank you very much.
Thank you. And thank you very much for listening to my talk. Thank you.